Right, so last time we were talking about gyroscopes, and I just want to finish up that discussion. Hopefully you guys took a look at the, oh, let me get rid of these. We don't need them here. Hopefully you guys took a look at the video that I mentioned last time, the Veritasium video. It's very, it's a quality video, so would recommend. Um, so the only thing that I wanted to finish talking about was just how we can figure out the period of the period of gyroscopic precession. So perhaps we understand now why it happens, and that's just because the torque that's applied due to gravity on the gyroscope is perpendicular to the angular momentum, and therefore it leads it to go in a circular motion, but that doesn't necessarily explain what the period is. So what we're going to do is we're going to analogize to understand the period of the gyroscopic precession. So for regular circular motion, we can find the period relatively easily. Here, let's say that we have an object going around in a circle at some speed from the center. So our object at that point in time has momentum that's pointing that way, and the force that's pointing inward. And that's what's called, that is what causes the precession. The fact that because the momentum, P, is perpendicular to F, we get circular motion. And another way of phrasing this is because the velocity is perpendicular to the acceleration. Oh, you're right, I think it is. Is that better? Okay. Right, so because the velocity is perpendicular to the acceleration, that means that we get circular motion. And that's not surprising because the centripetal acceleration is always perpendicular to the velocity, right? That's just a fact. And so that's what causes circular motion. However, the force, which is equal to MAC, centripetal acceleration, let's just talk about magnitudes here. This can be written as m times v squared over r, which is just m times v times 1 over r times v, right? All I did was simplify a little bit. I'm just writing out a formula for the force. And so this is equal to the magnitude of the momentum times 1 over r, and the speed v, well, that is the speed is just the distance traveled, 2 pi r, divided by the period, right? So this is just 2 pi r divided by the period. And so this is just equal to p times 2 pi over the period. So what we find then is we find that the period, t, not tension, is 2 pi times the momentum divided by the force. And these are magnitudes. And so we actually didn't have to know anything about how the force, or like, all we had to know was the momentum and the force. And so because this expression only relies on the fact that the momentum and the force are perpendicular to each other, it relies on some other facts, but this statement is true regardless of those facts, we can just figure, and we understand that gyroscopic precession happens for the same reason, i.e. angular momentum is perpendicular to the torque. We can use the same reasoning, just swapping out the variables. So for gyroscopic motion, what we find is, again, so let's draw our dotted circle for the path traveled, and now we have our gyroscope with maybe like the ends sticking in and out and whatnot. So in this case, and now it's, well, let me draw a smaller circle so that way then it's more realistic. So it's like this. In this case, L points this way, and the torque also points that way, just like in the, or very, very similar anyway, to the momentum and force understanding that we had of circular motion. And so again, we have that the torque, which plays the role of force for rotational motion, is perpendicular to the angular momentum, which plays the role of translational momentum for rotational motion. And so precisely using the same logic, we then have that the period of the precession, not the rotation rate of the gyroscope itself, is, oh, what just happened? That was weird. Is 2 pi times L over tau. And you can check the units, it checks out. And so for a wheel or a hoop with axis length r, axis of length r, that's this distance here. Well, the torque is just mg times r. Looking up here, we computed the torque. It's just the distance from the center of the gyroscope to the pivot point. In this case, the pivot point is the point it's going around, and it's just multiplied by mg. So we have mgr. Oop, it zoomed in a little bit. And I is just, well, it's a hoop, so it has moment of inertia mr squared, where r is the radius of our gyroscope. And so now we can just plug in values. So, well, actually, this implies that L is equal to mr squared omega. So now we can plug in values. So that means that the period is 2 pi times m, that's not an m, that's an r, times mr squared omega, divided by m, that should be a capital M, because it's the same mass, mgr. R is the distance, is the length of the axis, or the axle. And so simplifying, you get that this is 2 pi times the radius of your hoop squared times the angular velocity of your hoop, divided by g times r, where r is the distance from the center of your gyroscope to the axis of rotation. And this is just now a formula that describes gyroscopic precession. It's kind of complicated, right? Like it's not certainly not something I would have guessed, but all we did was we just analogized from standard circular motion, and we used what we knew about the torque and the angular momentum of a spinning hoop. So r is the distance. So if we go back and we look at the bigger picture, r is this distance. It's the distance from the center of the hoop, the center of our gyroscope, to the pivot point, which is the length of the axis, the length of the axle. So let me draw a picture just to be a little bit more clear. So if this is our gyroscope, this distance is little r, this distance is capital R, and it has mass m. I think that should clear things up. And then that angular velocity is omega. All right, so we're going to change gears here pretty significantly. We're done with rotational motion. Well, okay, we'll use it again, but we're done covering new material. We're going to switch gears to talk about gravity. So we have a lot to talk about. I don't know how far we'll get. So this may or may not be our last topic, depending on how long it takes to cover all of the material I want to cover regarding gravity. If we finish gravity, then we'll get to harmonic motion, but that's neither here nor there. So far, we've kind of assumed a lot about the gravitational force. I've kind of just told you that it's mg. I told you that everything experiences the same gravitational force downwards on Earth, and it has an acceleration of 9.8 meters per second squared. Now we're going to answer why that's the case. So first question, why is the force of gravity on Earth mg? In magnitude anyway, right? It has direction too, but why is that the case? We're also going to answer how does this gravity this mg gravity, relate to the gravity that makes the planets go in circles or orbits? Like, how are they related to each other? How are they the same thing? And finally, well, it'd be nice, but a question you also might have is just how does it work? Like, what actually is happening? So in this course, we're going to answer the first two. Unfortunately, the third question, well, A, it's kind of vague, and B, it's still not fully understood by, you know, professional scientists. Like, it's not well understood. Our best understanding is Einstein's general relativity, which you may have seen these images with like a sheet of rubber and like stuff sitting on it. That's our best understanding, but it's probably not correct. So, but we'll definitely understand the first two questions. At least that's the hope. So the way that we're going to answer these two questions is by invoking or learning about Newton's law of universal gravitation. So what is Newton's law of universal gravitation? Well, it's a set of, you could write it quantitatively, which we will get to in a minute, but it's a set of hypotheses or statements about gravity. So the first statement is that gravity is a force that acts between two objects. Only two objects, but every two objects. What I mean by that is if you want to find the gravitational force from one object on the other, well, then there's a way to calculate that. It doesn't depend on a third object, it only depends on those two objects. But if you want to find, say, the net gravitational force on a single object, you'd have to find the gravitational force from every other object on that object that you're interested in. You'd have to worry about every single pair. Another statement about gravity, gravity is always attractive. I.e., there's no such thing as anti-gravity, at least according to Newton's law of universal gravitation. Third, perhaps this is not surprising, gravity obeys Newton's third law. So that means that if object 1 is applying a gravitational force to object 2 will apply an equal and opposite gravitational force to object 1. Fourth thing is a set of quantitative ways, or is a set of ways to characterize the magnitude of gravity. The magnitude depends only on, I suppose, three things, but I'm gonna say two things. The first is the mass of the two objects. Meaning it will depend on both the mass of the first object and the mass of the second object, and the distance between the objects. Now, the first relationship, that it depends on the mass of the two objects, in particular, it is proportional to the product. Just trying to simplify this. Proportional to m1 times m2. The way that the gravitational force depends on the distance between the two objects is that it follows an inverse square law. So the first one kind of makes sense. If you double the mass of one of your objects, it's going to have double the gravitational pull. If you double the mass of both of your objects, they will have quadruple the gravitational pull towards each other. This distance between the objects following an inverse square just means that if you double the distance, the force weakens by a factor of 4. If you triple the distance, the force weakens by a factor of 9, and so on. So there are consequences of these facts. So the first is, and perhaps I won't write this down, but the first is sort of obvious. It's just Newton's third law. If the Earth is pulling on a, say, 50-gram apple, or that's a really heavy apple. Let's say that the Earth is pulling on an apple with a force of 5 newtons. So still a heavy apple, but whatever. Then the apple pulls back on the Earth with a force of 5 newtons, a la Newton's third law. Meaning that when the Earth causes something to fall to the ground because it is applying a gravitational force to that object, the object is also a little bit causing the Earth to fall towards it, just significantly less because it has a lot more mass. So other consequences, mathematically speaking, are these last statements. The force of gravity is proportional to mass 1 times mass 2. The force of gravity is also proportional to 1 over r squared, where r is the distance between the two objects. And so we can combine these two formulas to get the following. The force of gravity is proportional to the product of their masses divided by the distance between them. So what this means, the fact that it's proportional to it, just means that we can write this as an equality if we just introduce a constant. So that means that there is some number call it g, which is just some constant, such that the following is true. The force of gravity, or the magnitude of the force of gravity anyway, is g times m1, m2 divided by r squared. So this is the formula for the magnitude of Newton's of the gravitational force according to Newton. Now, this number is a priori not determined, right? Like that's something that Newton's law of gravitation doesn't determine, right? All we have is just these relationships. That doesn't tell us what that constant is, but you can determine that constant empirically. You can go out, you could measure, say, the mass of 2 very large, heavy lead balls, and then you can measure the very, very small gravitational force between them. This is known as the Cavendish experiment, by the way. It was done in the 1800s. And you could use that to calculate the gravitational force experimentally. And so what we determined with better and better measurements is that g, which is known as Newton's constant, is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Now that should make sense. The units should make sense. We want g to cancel out the units of the radius squared, and we want to cancel out the units of the kilogram squared in the numerator. So, and it should output a force which has units of newtons. So that's just the value of g. It just is that number, or approximately that number anyway. And that's what you use when you want to calculate the magnitude of Newton's, or of the gravitational force. Now, we also mentioned that the direction of the gravitational force, well, we mentioned something about that. We mentioned that it's attractive. So what does that mean? That means that it points from up, or it points to the, how do I want to phrase this? It points in the direction of the attracting object. So I'll give an example. And this is typically how we'll handle these types of things. Let's consider object 1. And by the way, I'm just going to be referring to these things as object 1 and object 2, because that kind of coincides with mass 1 and mass 2. They're just two things with mass that are attracting each other. So consider the first object as the source, putting source in quotes because it doesn't really make a whole lot of sense, of your force. So if you want to figure out the direction So does there exist a minute force of gravity between you and your home and me? And yes, there does. There exists. So think of midichlorians. It is a force that connects all things, except it's real and not a terrible write-in into a set of prequels that were all awful. But yeah, there's a gravitational force between any two things in the universe. Right, so consider the first object as the source of the force, and the reason we're doing that is because we're interested in computing the direction of the force on the second object. So we're going to consider the first object as the source of your force. Where was I? And so to do that, we're going to make it the origin of the coordinate system. So let's say that we have our coordinate system, or let's say that we have our object 1. This is our source. So I'm just going to draw a coordinate system on top of it, make it the origin. And then maybe object 2 was over here. This is, say, the recipient of the force. Well, we know how to figure out the unit vector or we know how to figure out the vector that goes from the origin to the point. It's just the coordinates of the point itself is that vector. And so the vector r hat, which is this vector here, this is the unit vector pointing away from the source. So you would find the vector pointing away from the source, and then you just divide by its magnitude. This is the position vector, or the it's in the same direction of the position vector. In this coordinate system. So I chose a coordinate system, putting the source at the origin. I didn't have to do that, but the unit vector r, when we're talking about gravity, is always the unit vector that points from the source to the recipient. So then what direction is toward the attracting object? So we expect gravity to point that way, right? For the force on the recipient. So that means that the direction of an attractive force, any attractive force, in fact, is the vector negative r hat, right? You can always specify a direction as a unit vector, and so that's what I'm doing here. So we can combine the direction and the magnitude to get a formula for the force due to gravity. Formula for the force due to gravity is negative g m1 m2 over r squared times r hat. And by the way, note that I'm being consistent with my notation. This r hat, this is the vector r divided by the magnitude r. And so that's just the vector r divided by r. So these r's refer to the same thing. It's just this is the length of the vector. The r without the vector symbol is the length of the vector, and r hat is the unit vector pointing in that vector's direction. So here's our formula. And it's a powerful formula. That's how we got to the moon. Right? We just used Newton's laws to get us to the moon. It was sufficient. And they did that in the 60s without calculators, so more power to them. Are inverse square laws determined experimentally? That's a good question, actually, and it's a deep question. To a certain extent, yes, but if everything we know about physics makes sense, then it's sort of a natural consequence of the fact that our universe has 3 dimensions, 3 spatial dimensions anyway. So you could have predicted that our universe has that all of the like the electromagnetic force is also an inverse square law. You could have predicted that these are inverse square laws. However, you always want to check your predictions, and we can check experimentally whether or not these forces obey the inverse square law. And in fact, they do, up to some absurd degree of precision. But actually, you'll learn about where this inverse square law comes from in 9C. It requires a little bit more calculus than you have. So you'll just have to trust me on this one for now. Right, so this law only applies to point masses. I mean, so far we haven't talked at all about extended objects. I did not mean to cross that out, I meant to underline it. Right, because if you have an extended object, then the distance that each part of that object is from the object that it's being attracted to changes, right? They will be at different places. Now, in previous lectures, I said that the force of gravity just acts at the center of mass. But that's not generally true. It's only true for, sorry, that is generally true. But it doesn't mean that the formula for gravity is the same as if all of the mass were at the center of mass. So, however, there is an out here. It turns out, so in general, dealing with extended objects is hard. It requires integral calculus. I mean, I suppose it's not hard, but it's more than what you have. However, there is a nice consequence of, again, more calculus that you don't have, that will let us still answer questions about extended objects in a very specific case, and that is the following exception. For spherically symmetric objects, gravity acts as if all of the mass was at the center of mass. So what I mean by that is that, let's say that you have a sphere, and the density of the sphere, it's not uniform, like a solid sphere, right? Ball. Maybe the density of the sphere isn't uniform, but the density is symmetrically, or spherically symmetric, meaning like the only thing that the density depends on maybe is the distance that the point is from the center of the sphere, i.e. if you rotate the sphere, nothing's going to change. Well, then you could just swap that out with just a point mass, with all of the mass at the center, where the center of mass is. And gravity treats those two things precisely identically, at least Newton's second law does. Sorry, Newton's law of gravitation, of universal gravitation. And again, that's a result of calculus that's not so hard to prove, but it's again beyond what you guys have yet. You'll learn it in, I think, 21C, or maybe 21D, or whichever one is multivariable calculus. You'll learn about doing that there. But it's a nice, convenient fact, because a lot of the things we care about, like the Earth, like the sun, like the moon, all of these things are very nearly spherically symmetric. And so we can still apply this formula to those things. I.e. we just treat the object as if all of its mass were concentrated at its center of mass. And so then you would use this value of r would be the distance between the center of masses of those objects. As a picture, let's say we have this, that's not a very good circle. Let's say that we have the sun here. This is, of course, not to scale. And let's say we have the Earth here. Well, how would you find the distance that you use for Newton's law? Well, you would find where the center of masses are, and you would just, dang it, it's so close. This distance here, the distance between the center of masses, is the distance you would use for r. You wouldn't use the distance from the surface to the surface. You would use the distance between the center of masses, and those occur at the center of spherically symmetric objects. So, okay, that gives us something. And now we should sort of have the tools to figure out what's going on with gravity on Earth. So let's do that. How does the force due to gravity being, or actually we can just write the vector notation, being equal to negative g m1 m2 over r squared in the r hat direction, relate to the formula that you've been using, which is just mg? Well, so in principle, to calculate the force due to gravity from the Earth on an object, we need to know a few things. We need to know 3 things, actually. We would need to know the following. We need to know the mass of the Earth. That would be maybe m1. We need to know the mass of the object. And we need to know the distance between their center of masses. I.e. the center of mass of the Earth and the center of mass of the object. Now, by the way, you might object that not all objects that we act gravitationally on with the Earth are spherically symmetric, so how can we apply this rule? But consider the size of the Earth, and consider that relative to the distance that the object is from the center of the Earth, any normal-sized objects will be basically point masses. So in fact, it's sufficient to just say the distance from the center of mass of the Earth to some point on the object, because the object is very, very small relative to that distance. So our magnitude, which is what this mg represents, it's a magnitude, would be g times the mass of the Earth times the mass of the object divided by this r squared. And so you might wonder how you get mg from this. Well, let me write a header. Fortunately, if all we're worried about is the Earth, for any object on the Earth, like if we're only worried about the gravitational effect of the Earth on an object, this quantity, g times the mass of the Earth, is always the same, right? It's always the force of the Earth pulling on the other object. And so if we just know what that number is, we can just plug that in and just get a number. It doesn't matter where your object is, what your other object is. G m sub e, g times the mass of the Earth, is always going to be the same. And this is known as the gravitational parameter of the Earth. And every celestial body has a known gravitational parameter. And it's just g times its mass. And the value for this is about 3.986 times 10 to the 14th meters cubed per second squared. It's just a number. You just take the mass of the Earth, which is really, really big, you multiply it by g, which is really, really small, and you get something else that's still really, really big, because the mass of the Earth is really, really big. So the mass of the Earth can be estimated in several different ways. Basically, once you know what g is, like if you reliably know what the mass of, sorry, let me backtrack a little bit. This gravitational parameter for the Earth, and actually for all of the other bodies in the solar system as well, those were known long before we knew the mass of the Earth and the gravitational constant g. Because as long as you can calculate the force on the Earth and the mass of whatever object you're interested in, and the radius of the Earth, this is just a variable that you can solve for. And so this has just been a known quantity for, a few hundred years. Once Cavendish determined a way to determine the a way independent of the Earth's mass to determine what Newton's constant was, g, by using just 2 very large lead balls in a very good experiment, then you could use that value of g to solve for the value of m using the gravitational parameter. I imagine that there are probably other ways that you can estimate the mass of the Earth. However, at the end of the day, we can't put the Earth on a scale, so it's always just we're measuring the mass of the Earth by measuring a force and then calculating using Newton's laws. It's not something that can be explicitly measured, I don't think. Right. So another useful fact that comes from this is that on the surface of the Earth, we know the distance from the center of mass of the Earth to the object. It's just the radius of the Earth. It's the distance from the center of the Earth to the surface. This value of r is just the radius of the Earth, or it's approximately the radius of the Earth, which is just, for definition's sake, and that is approximately 6.378 times 10 to the 6th meters. Now, before I get another question about this, the radius of the Earth has been known for 2,500 years. It was determined by the Greeks to pretty good precision, within 10% or so, and it was basically calculated using a very clever arrangement of sticks in wells and shadows. Because if you know the distance between 2 points and you assume the Earth is a sphere, and then you can calculate the radius of the Earth based off of the angles that various shadows make at the same time of day. If you use, like, given some latitudes and things like that, it's just a geometry problem at that point. And so that was determined, a long time ago. How did they know the Earth was a sphere? Because, well, it certainly wasn't flat, because, oh, I should clarify. If you're a flat earther, leave. You don't get to pass this class. Right, but they knew the Earth was a sphere at the time because they still had sailing ships, and so they could see the ships disappearing below the horizon. And they also noticed that people would, or that the angle of shadows would be different at different places of the Earth. And like there's a whole bunch of evidence that we had. Further, they knew that the celestial bodies were round, so they had good reason to believe that the Earth was round, and so on and so forth. The Greeks were a lot smarter than people give them credit for. Like, Christopher Columbus didn't think that the Earth was flat. He just thought the Earth was a significantly smaller sphere than it turned out to be, which is why he was surprised that he reached the that he reached the Americas rather than India. Right. Let's continue. So we know the radius of the Earth, and so that will tell us the distance that an object is from the center of mass of the Earth, which is what we need to know to plug in. So for any object, let me move this down one line so I have room. So for any object with mass m on the surface of the Earth, by the way, the Earth isn't perfectly a sphere. It's called an oblate spheroid, but it's a good approximation. For any object with mass m on the surface of the Earth, then we can calculate the force, right? The magnitude of the force due to gravity would just be g times m sub e times the mass of the object divided by the radius of the Earth squared, which is just g times m sub e. This top term is the gravitational parameter of the Earth, and the bottom term is the radius of the Earth squared times m. So if we're not doing anything tricky, and now we can just plug in numbers. So, this is 3.986 times 10 to the 14th divided by 6.378 quantity squared times 10 to the 12th. 10 to the 6th squared is 10 to the 12th. And this is all in units of meters per second squared. You can check that the units check out, times the mass, which works out to be 0.098 times 10 to the 2 meters per second squared times m, which is, the ever familiar 9.8 meters per second squared times m, which is, approximately 10 meters per second squared, within 2% times m. That's where the value of g comes from. It comes from Newton's law of universal gravitation. It comes from plugging in the gravitational parameter of Newton's law, and it comes from plugging in the radius of the Earth. So, for example, if you knew the gravitational parameter of the Earth, and you knew the gravitational force on the Earth, and you assumed Newton's law, you could actually calculate the radius of the Earth if you wanted to, and you'd be pretty close. Now, so this tells us what the force is on a how do I want to phrase this? This tells us what the force is on a single object. But the next question might be, and this is just a side point. If two objects are falling from the same height, i.e. from the same rate, from the same initial distance from the Earth, it's not it seems to be the case that those objects fall or have the same acceleration. And you might say, of course they do, because if gravitational force is mg and force is equal to ma, then you can just cancel the m's, and therefore you get that the gravitational acceleration is always the same regardless of the mass. But this statement, that mg equals ma, didn't have to be the same, right? It could have been the case that there's one type of mass called, say, inertial mass that force is equal to, and it could have been another type of mass that shows up in the gravitational formula. It could have been that this is gm1 gravity, m2 gravity over r squared. They could have been different things. There's no reason to suggest that they had to be the same thing. And then you would find that a thing's inertial mass and gravitational mass, the relationship between the two would affect the rate at which they fall. Experimentally, at least to very good precision, it seems that they are the same thing, that inertial mass and gravitational mass are the same, and thus everything does fall at the same rate. But it's not well understood why that's true. Like the best science we have is just not there yet. We don't have an explanation for why inertial mass and gravitational mass are the same. So, you know, food for thought. If you can figure that out, go get your Nobel Prize. Okay, so what we did here is we calculated the gravitational acceleration, this value of lowercase g, for an object on the surface of the Earth. However, the astute amongst you may have noticed that, well, if the gravitational acceleration, this 9.8 meters per second squared, depends on the distance between the object and the center of mass of the Earth, wouldn't that mean if an object is thrown higher, it will have smaller gravitational acceleration? And the answer is, of course, yes, that is true. So let's just see what kind of an effect that might have. Let's suppose you throw a cannonball up 10 kilometers. You're like the strongest man in the world. You're stronger than the mountain or something. 10 kilometers is about the cruising altitude of a Boeing 747. So, you know, that's just about as high as most things that are going to go without going into space. You know, that's about the height of Everest and so on and so forth. So most things that are happening on the Earth where we use mg is valid as long, or they occur between 0 and 10,000 kilometers, or in 10 kilometers up. So what does that mean for our formula? What do we plug in for the distance? Well, that means that the distance r is just the radius of the Earth plus 10 kilometers, right? It's 10 kilometers further away from the center of the Earth than the surface is. And so then you can go and you can plug in this value. And it turns out that you get that the force due to gravity, the magnitude, is now 9.77 meters per second squared times g. And this is as opposed to 9.8. And so how much of an error is there here? Well, from the true value of 9.8, it's like 0.03, or sorry, like 0.3% error. Very, very, very small. And so that's almost negligible. But you might say, well, wait a minute, we use 10 meters per second squared in this class, which is what I told you to do. So how much is the error there? I mean, this is an easy calculation, but you know, it's worth pointing out that the error up to about the maximum error that we're going to get for any Earth-based gravitational things is about 2.3%. You know, there's going to be bigger errors in your measurements and in other factors that we're not accounting for, like drag. So the fact that we can use 10 meters per second squared for the gravitational acceleration, like on the surface of the Earth or near it, it's good enough. What about at the altitude of the International Space Station? Now, we know that the astronauts in the ISS experience something that we call 0G. You might expect then that G should be 0 there. Well, Of course it's not. The altitude of the International Space Station is about 400 kilometers up. By the way, the boundary between what we call the atmosphere and space is known as the Kármán line. It's about 100 kilometers up. So, you know, if you were driving at high weight speeds, you could go from the ground to space in about 2 hours. No, sorry, in about an hour. But you might expect that the gravitational force here would be very small. So what value do we use for r? Well, it's just the radius of the Earth plus 400 kilometers. So we go and we compute the gravitational force, and we find, perhaps unsurprisingly, that it's just 8.6, that should not be a g, that should be an m up here, I'm sorry, 8.68 meters per second squared times m. So it seems like what I'm telling you is that the astronauts in the International Space Station, you know, floating around making videos of water just floating in the air, would only weigh about 11% less than they would on Earth, because the gravitational force is only 11% weaker on them. So what gives? Why is it that we say that they're weightless, and why do they just float around if their gravitational acceleration is so high compared to what we might expect? So I think I'm actually going to stop there. This is a really good stopping point to leave you on a cliffhanger for Wednesday. And we'll talk about it then. So we got about as far as I expected. And we will continue. Yeah, Kwangla, so you're correct. The term is microgravity, but that's not what this is. This is not microgravity. This is only 11% smaller, right? Microgravity would be like 1% maybe. And yes, we do call it microgravity, but for a different reason. So we do not have class on Monday, no lecture on Monday, because I think it's Memorial Day or something like that. So so the homework is going to be due on Tuesday at noon. Late homework will still only be accepted by Wednesday at noon, but homework won't be due till Tuesday. So, and there's no discussion next week either for that same reason, because it's canceled because the university holiday. Oh, let me stop recording.